Redundancy sounds like common sense. If something fails, you want a backup. If the backup fails, you want another one. If lives are at stake, you want as many layers of protection as possible. In early spaceflight, this logic felt not just practical, but necessary. Spacecraft operated far from help, inside hostile environments with no margin for improvisation once things went wrong. The idea that a single component failure could end a mission or kill a crew was unacceptable, so systems were duplicated, then duplicated again. Power sources, sensors, communication paths, control logic. Redundancy became a promise, a reassurance that failure would not be final. But over time, engineers and operators discovered something uncomfortable. Redundancy did not simply remove risk. It changed the kind of risk they faced. A single failed system produces a clear signal. Two systems failing differently produce ambiguity. When redundant systems disagreed, the problem was no longer mechanical. It became interpretive. Which reading was correct? Which system was lying? Whether the disagreement mattered now or could be tolerated for later. Backups kept systems running, but they also created moments where no answer was obviously right. This was not a theoretical problem. Redundant sensors often produce conflicting data. Backup systems sometimes behave differently than primaries. Automatic switching logic introduced its own timing and failure modes. Crews and controllers were forced to decide not whether something had failed, but what failure even meant in that moment. Redundancy bought time. It also demanded judgment. As spacecraft grew more complex, redundancy multiplied interactions. More wiring meant more interfaces. More interfaces meant more ways for systems to influence each other. Each added backup increased survivability in isolation, but also increased the difficulty of understanding the system as a whole. This tension was not obvious at first. Redundancy felt protective. It encouraged confidence. It suggested that problems could always be contained by adding one more layer. In practice, it sometimes delayed recognition of serious issues by masking degradation. Systems kept working well enough to postpone intervention, even as margins quietly eroded. Early spaceflight did not abandon redundancy. It learned to be wary of it. Engineers began to realize that duplication without clarity could make systems harder to manage, not easier. That safety depended less on how many backups existed and more on whether people understood what those backups would do when reality diverged from expectation. This episode examines why redundancy was never a simple solution, how it reshaped decision-making under pressure, and why adding more protection sometimes made spacecraft more fragile instead of safer. Not because redundancy was a mistake, but because safety in complex systems is built on understanding, not accumulation. Part 1. What redundancy actually meant in early spacecraft. Redundancy in early spacecraft was not a single idea. It was a collection of strategies applied unevenly, shaped by what engineers feared most at any given moment. At its simplest, redundancy meant duplication, two power sources instead of one, multiple sensors measuring the same variable, backup communication paths in case the primary failed. This kind of redundancy was intuitive and visible. It mapped cleanly onto the fear of single-point failure. But as spacecraft grew more complex, redundancy became more nuanced. Some systems were backed up identically. Others were backed up with different designs intended to fail in different ways. Some backups were always active, operating in parallel with primaries. Others were dormant, waiting to be switched on manually or automatically when something went wrong. Each of these choices carried different implications. Identical redundancy, simplified, training and maintenance, but it also meant that shared design flaws could affect both systems at once. Dissimilar redundancy reduced the risk of common mode failure, but introduced complexity in operation, interpretation, and verification. Active redundancy provided continuous protection, but increased the chance of disagreement between systems. Standby redundancy reduced noise, but relied on successful detection and switching at exactly the right moment. Redundancy was never free. Every additional system increased mass. Every added wire increased routing complexity. Every new interface created another place where signals could be delayed, distorted, or misinterpreted. These costs were not theoretical. They showed up in testing, in integration, and in the growing difficulty of understanding how the spacecraft behaved as a whole. Early spacecraft were already operating near the edge of what could be analyzed exhaustively. Adding redundancy pushed them further. This is where a quiet shift occurred. Redundancy stopped being purely a design decision and became an organizational one. Engineers were no longer asking only whether a system should have a backup. They were asking who would interpret conflicting data, how disagreements would be resolved, and how much ambiguity crews and controllers could handle under pressure. A redundant system that required complex judgment to use safely transferred risk from hardware to people. That transfer was not always acknowledged explicitly, but it was real. In many cases, redundancy was added late in development as a response to identified vulnerabilities. A sensor that drifted too much was backed up with another. A power path that seemed fragile was supplemented with an alternate route. Each addition made sense in isolation. Together, they reshaped the system. The spacecraft became more capable, but also harder to reason about. Understanding how it behaved required not just technical knowledge, but familiarity built through repetition. Crews and controllers had to learn which disagreements mattered and which could be ignored. They had to develop intuition about patterns that no document could fully capture. Redundancy also created a subtle psychological effect. Knowing that backups existed changed how people thought about margins. Systems were sometimes pushed harder because there was a fallback. Anomalies were sometimes tolerated longer because nothing had failed outright. Redundancy softened urgency even as it increased complexity. This did not mean redundancy was a mistake. It meant redundancy changed the nature of risk. Instead of asking, "What happens if this fails?" teams increasingly had to ask, "What happens if this and its backup disagree?" Instead of preparing for clean failures, they prepared for ambiguous ones. Instead of responding to loss, they responded to contradiction. By the time early space programs accumulated experience, redundancy was no longer viewed as a simple safety multiplier. It was understood as a trade. It increased survivability while demanding interpretation. It reduced certain failures while introducing others. It protected hardware while taxing judgment. Understanding that trade is essential, because the real challenge of redundancy did not appear when systems failed completely. It appeared when they almost failed, differently, at the same time. That is where the next problem emerged. Part 2. When redundant systems disagreed, a complete failure is unmistakable. A system stops responding. A signal disappears. Power drops to zero. The problem announces itself, and the response, while urgent, is usually clear. Procedures exist for loss. Training anticipates absence. Disagreement is harder. When redundant systems disagreed, nothing was obviously broken. Data continued to flow. Readings updated. Indicators stayed alive. What failed was coherence. Early spacecraft encountered this problem repeatedly. Multiple sensors measuring the same variable would return different values. Two power paths would show acceptable performance, but not the same performance. A primary system and its backup would both appear functional, yet behave differently under load. None of these situations fit cleanly into failure checklists. The question was no longer, what failed? It became, which version of reality is correct? This shift mattered because disagreement consumes time. Crews and controllers had to slow down, compare signals, and interpret context. They had to decide whether the disagreement itself was dangerous or merely inconvenient. Acting too quickly risked shutting down a healthy system. Waiting too long risked allowing a real problem to deepen. Redundancy replaced certainty with choice. In some cases, systems used voting logic. If 2 out of 3 sensors agreed, the third was assumed to be wrong. This worked well when failures were clean and independent. It worked less well when systems drifted gradually or responded differently to environmental changes. A sensor that aged slightly faster than others might not fail outright. It would simply disagree more often. Voting logic would exclude it, even if it was the most accurate under certain conditions. Redundancy did not eliminate judgment, it embedded it. Automatic switching systems introduced another layer of complexity. Some spacecraft were designed to shift from primary to backup automatically when thresholds were crossed. This reduced reaction time, but it also created new questions. Did the system switch because the primary failed, or because the threshold was poorly calibrated? Was the backup now operating inside conditions it had not been designed for? Should the system be switched back or left alone? Each automated response still required interpretation. When automation behaved unexpectedly, crews had to decide whether to trust it or override it. That decision was rarely obvious. Automation was fast, but blind to context. Humans were slower, but capable of reasoning about the situation as a whole. Disagreement also strained communication. Different teams focused on different signals. Engineers watching thermal data saw one story. Flight controllers monitoring power saw another. Crews experienced something else entirely through physical cues and timing. Redundancy multiplied perspectives. Aligning those perspectives under time pressure was difficult. Misalignment did not require incompetence. It emerged naturally from complexity. Importantly, disagreement did not always mean danger. Some discrepancies resolved on their own. Some reflected normal variation. Some indicated deeper issues that unfolded slowly. The challenge was knowing which was which without the benefit of hindsight. This uncertainty taxed decision-making. Redundant systems demanded that people make interpretive choices repeatedly, often without clear confirmation. Each choice carried consequences, and the absence of immediate failure did not guarantee correctness. Over time, teams learned to recognize familiar patterns. They learned which disagreements mattered and which did not. They learned when to intervene and when to wait. But this learning was experiential, not procedural. It depended on exposure, repetition, and trust. It could not be fully captured in documentation. New team members had to acquire it gradually, often by watching how experienced operators responded. This made redundancy a social challenge as much as a technical one. The presence of multiple systems increased the need for coordination, shared mental models, and disciplined communication. Without those, redundancy amplified confusion instead of preventing failure. This is why redundancy did not behave like a safety net. It behaved like a lens. It brought certain problems into focus while blurring others. It protected against abrupt loss, but created gray zones where interpretation mattered more than detection. Understanding this is essential, because disagreement was not the only way redundancy complicated safety. In some cases, redundancy changed behavior long before anything went wrong. That effect was quieter and in many ways more dangerous. Part 3. How redundancy changed behavior before anything failed. Redundancy did not only affect what happened during failures, it quietly reshaped behavior long before any system broke. The presence of backups altered how people thought about margins, urgency, and acceptable deviation. When a system had no fallback, attention sharpened naturally. Limits were respected because consequences were immediate. When backups existed, the boundary between safe and unsafe became less distinct. This was not carelessness, it was human. Knowing that another system stood behind the primary changed how operators interpreted warning signs. An anomaly that might have demanded immediate action in a single-string system could be deferred when redundancy existed. The logic was simple and often reasonable. If the primary degraded, the backup would take over. But that logic carried assumptions. It assumed that degradation would be obvious. It assumed that switching would be clean. It assumed that the backup would behave as expected when called upon. In practice, redundancy sometimes delayed recognition of serious problems. Systems continued to function well enough to avoid triggering alarms even as underlying conditions worsened. Margins were consumed gradually. By the time a failure became undeniable, fewer options remained. Redundancy created a buffering effect. That buffer bought time, but it also reduced urgency. Decisions that might have been made early were postponed. Intervention thresholds drifted. What once felt abnormal became tolerated because nothing had failed outright. This drift was subtle. Teams did not decide to ignore limitations. They adjusted expectations based on experience. When a system survived past anomalies without consequence, confidence grew. The absence of failure was interpreted as evidence of robustness. Over time, this confidence changed how systems were used. Redundant systems were sometimes pushed closer to their limits because there was a belief that protection existed beyond the primary. Loads increased. Operating windows narrowed. Conditions that were once avoided became routine. None of this required explicit approval. It emerged from success. This is where redundancy interacted with culture. Organizations that emphasized caution treated redundancy as insurance to be used sparingly. Organizations under schedule or performance pressure were more likely to treat redundancy as capacity. The same technical architecture supported different behaviors depending on incentives and expectations. Redundancy also influenced how anomalies were explained. When something odd occurred in a redundant system, it was easier to attribute it to noise or mismatch rather than danger. After all, the backup was still available. This framing reduced anxiety, but it also reduced curiosity. Questions that might have been pursued aggressively in a single system design were sometimes deferred. The system was still functioning. There was time. Other priorities pressed. This is how redundancy can mask degradation, not by hiding data, but by changing how data is interpreted. When systems appear resilient, warning signs are discounted more easily. The line between acceptable variation and meaningful deviation becomes blurred. Importantly, this effect was not universal. Teams that were trained to treat redundancy as a last resort rather than a cushion were less vulnerable to this drift. Where redundancy was framed as time buying rather than problem solving, attention remained sharper. But maintaining that framing required discipline. It required leaders to reinforce that backups were not substitutes for understanding. It required training that emphasized early recognition rather than late recovery. It required resisting the temptation to equate survival with safety. Redundancy did not remove responsibility. It redistributed it. Operators still had to decide when something mattered. Managers still had to decide when to intervene. Engineers still had to decide which anomalies deserved investigation. Redundancy changed the stakes of those decisions. By delaying consequences, it increased the risk that decisions would be made later, under worse conditions, with fewer options. This is the paradox at the heart of redundancy. It protects systems from immediate failure while increasing the importance of judgment over time. It reduces the frequency of crisis, but raises the cost of misinterpretation when a crisis finally arrives. Understanding this paradox explains why redundancy alone could never guarantee safety. And it sets the stage for the moments when redundancy did not just complicate behavior, but actively increased risk. Part 4. When redundancy increased risk, instead of reducing it. There were moments in early spaceflight when redundancy did more than complicate decision-making. It actively increased risk. This happened not because backups failed, but because they interacted with people and procedures in ways that the system was not prepared to manage. One common problem was mode confusion. As redundant systems multiplied, spacecraft accumulated multiple operating states. Primaries, secondaries, automatic modes, manual overrides, degraded modes. Each state altered how the system behaved and how data should be interpreted. In theory, these modes were well defined. In practice, transitions between them were not always obvious. A system might appear to be operating normally while quietly relying on a backup. Indicators did not always make this clear. Crews and controllers sometimes believed they were monitoring one configuration while the spacecraft was actually in another. This was not negligence. It was a consequence of complexity. Redundancy expanded the number of possible system states faster than documentation and training could fully capture. Under time pressure, people reasoned from expectations. When reality diverged subtly, errors became easier to make. Another risk emerged during switching. Switching from a primary system to a backup was often treated as a discrete event. In reality, it was a process. Loads shifted, transients appeared, timing changed. A system that was stable before switching could become unstable during or after it. Switching itself became a hazard. In some cases, crews hesitated to switch because they feared the consequences. In others, switching occurred automatically, forcing people to react to a new configuration without fully understanding what had changed. Both situations were dangerous. Redundancy also increased the chance of conflicting actions. Different teams might respond to the same situation based on different assumptions about which system was active. A crew might protect one component while controllers tried to protect another. Actions that made sense individually could interfere with each other. Coordination mattered more than ever. But redundancy made coordination harder. Each additional system added another perspective. Each perspective added another interpretation of what safe meant in that moment. Aligning those interpretations required communication, trust, and shared understanding. Under stress, those qualities were fragile. In some cases, redundancy produced what looked like safety but functioned like fragility. Systems continued operating past points where intervention would have been safer because nothing had failed outright. By the time intervention became unavoidable, conditions were worse. Margins were thinner. Options were fewer. Redundancy delayed failure but did not prevent it. This delay was not neutral. It changed the context in which decisions were made. Late decisions are harder than early ones. They involve higher stakes, compressed timelines, and less flexibility. Redundancy also complicated accountability. When a single system fails, responsibility is clear. When multiple systems behave inconsistently, responsibility becomes diffuse. Was the issue design, operation, interpretation, communication? Often, it was all of them. This made learning harder. Failures involving redundancy were more difficult to analyze and explain. They resisted simple narratives. They challenged the assumption that adding protection necessarily improves outcomes. Early spaceflight did not immediately recognize these patterns. It took experience to see that redundancy could create failure modes that did not exist in simpler systems. It took humility to admit that adding backups sometimes made spacecraft harder to fly safely. Eventually, programs began to adapt. They reduced unnecessary duplication. They simplified switching logic. They clarified authority when systems disagreed. They trained explicitly for disagreement rather than failure. Redundancy was not abandoned. It was disciplined. That discipline was the difference between redundancy as protection and redundancy as liability. Understanding how that discipline developed leads to the most important question of the episode. If redundancy could both protect and endanger, what separated the systems that benefited from it from those that did not? That is where the story turns toward how redundancy was actually used well. Part 5. How redundancy worked when it was used well. Redundancy did not fail early spaceflight. Undisciplined redundancy did. The systems that benefited from backups were not the ones with the most duplication. They were the ones that treated redundancy as a limited resource rather than a universal solution. Where redundancy worked, it was paired with clarity, restraint, and an honest understanding of what backups could and could not do. The first distinction successful programs made was conceptual. Redundancy was not there to solve problems. It was there to buy time. Backups were treated as a way to preserve options, not replace judgment. Their purpose was to prevent immediate loss, not to make decisions easier. This framing mattered because it shaped how people responded when redundancy was activated. When a backup engaged, attention increased rather than relaxed. The system was considered degraded, not protected. Teams shifted into a more conservative posture, monitoring closely and avoiding additional stress until understanding caught up with reality. This prevented a dangerous assumption. Redundancy was not a sign that everything was fine. It was a signal that something had already gone wrong. Successful programs made this explicit in training. Crews and controllers were taught that switching to a backup was not a victory. It was an admission that margins had narrowed. Simulations reinforced this mindset by treating redundant system scenarios as high-attention events rather than recoveries. The goal was not speed. It was coherence. Another critical factor was authority. When redundant systems disagreed, someone had to decide which interpretation would guide action. Programs that handled redundancy, well-established, clear decision ownership in advance. Roles were defined. Escalation paths were explicit. This reduced paralysis. Instead of debating endlessly, teams could align around a single interpretation long enough to act. That interpretation could later be revised, but in the moment, unity mattered more than perfection. Clarity of authority did not mean rigidity. Experienced operators were still encouraged to challenge assumptions and raise concerns. But challenges were surfaced through structured channels rather than improvised debate during critical moments. Redundancy also worked better when systems were simplified rather than multiplied. Some programs deliberately chose fewer backups that were well understood instead of many that were poorly integrated. They accepted certain single-point vulnerabilities to reduce ambiguity elsewhere. This was counterintuitive. Giving up redundancy felt like increasing risk. In practice, it often reduced it by making system behavior easier to interpret under stress. A simpler system with clear failure modes could be safer than a complex one with overlapping protections. Training played a decisive role. Programs that managed redundancy effectively focused on recognition rather than response. Crews were trained to identify when redundancy was masking a deeper issue. Controllers practiced distinguishing between benign disagreement and meaningful divergence. This kind of training emphasized pattern recognition over procedural compliance. People learned what redundancy looked like when it was healthy and when it was not. They learned which disagreements resolved on their own and which required intervention. They learned to resist the false comfort that backups provided. Communication discipline mattered as well. Teams developed shared language for describing redundant system behavior. Instead of vague reassurances, they used precise descriptions. Instead of minimizing discrepancies, they highlighted them. This kept attention calibrated. Redundancy became safer when it was treated as part of the system's operating personality, not as a safety blanket. It was acknowledged, respected, and constrained. In these environments, redundancy supported judgment instead of replacing it. It gave teams time to think without pretending that thinking was no longer necessary. It preserved options without obscuring reality. That balance was fragile, but when it held, redundancy did what it was supposed to do. It prevented immediate catastrophe while keeping people engaged with the system's actual condition. This is why redundancy succeeded only when it was paired with humility. Humility about what systems could guarantee. Humility about what people could know in real time. Humility about how easily protection could become illusion. With that humility in place, redundancy became a tool rather than a promise, and that distinction leads directly to the final lesson of the episode. Part 6. What redundancy ultimately revealed about safety. Redundancy did not fail because it was poorly designed. It failed when it was misunderstood. Early spaceflight revealed that safety is not something that can be added layer by layer until risk disappears. It is something that emerges from how systems, people, and expectations interact over time. Redundancy changed those interactions in ways that were not always visible and not always intuitive. What redundancy offered was continuity. What it demanded was interpretation. It allowed systems to survive initial failures without collapsing. It bought time when time mattered most. But it also introduced ambiguity, delayed recognition, and shifted responsibility from hardware to judgment. When those shifts were acknowledged and managed, redundancy strengthened the system. When they were ignored, it made failure harder to see and harder to stop. This is the uncomfortable truth redundancy exposed. Safety does not come from accumulation. It comes from alignment. A system with many backups but little shared understanding is fragile. A system with fewer protections but clear behavior can be resilient. The difference lies not in how much protection exists, but in how well people understand what that protection actually does. Early spaceflight learned this slowly. It learned that backups do not replace attention, that protection does not eliminate responsibility, that survival after failure is not the same as safety before it. Redundancy worked best when it was treated as a signal rather than a solution, a signal that something had changed, a signal that margins were narrower, a signal that caution, not confidence, was required. When redundancy was treated this way, it sharpened awareness, it focused judgment, it preserved coherence under pressure. When it was treated as insurance, it dulled attention and encouraged risk to accumulate quietly. This lesson extends beyond spacecraft. Any complex system that relies on duplication without understanding invites the same failure patterns. Backups that are not understood create confidence without clarity. They postpone consequences without preventing them. The systems that endure are not the ones with the most protection. They are the ones that make risk legible. Early spaceflight did not succeed because it eliminated failure. It succeeded because it learned to recognize when protection was becoming illusion. That recognition required discipline. It required humility. It required an ongoing willingness to ask whether safety still meant what people believed it meant. Redundancy forced that question, and in answering it, space programs learned something far more important than how to build backups. They learned how easily safety can be mistaken for comfort. In the next episode, we will look at another assumption that early spaceflight quietly overturned: the belief that technology, not money, was the primary force shaping missions, and how budget constraints defined what was built, what was flown, and what was never attempted. Subscribe to continue exploring how space programs actually worked when ideal options were not available. Each episode examines one constraint and the systems built to live inside it.